Hello, now we are going to discuss about some important questions for the examination point of view. So those questions they're asking repeatedly, okay, repeated times, scam many times. So already you know about that you have various coordinate systems. We have three different types of the coordinate systems. Cartesian coordinate system, then you have cylindrical coordinate systems, and third one is the spherical coordinate systems. So here sometimes maybe question is very important about spherical coordinate systems. The question might be like this that you have to write about the spherical coordinate system. So a spherical coordinate system is it has parameters r, theta and phi. So this r, theta and phi having what is the range of this r, theta and phi, that is important. Okay. So this r is going to be changed from the 0 to infinity, and theta is going to change from 0 to pi, and phi is going to change from the 0 to 2 pi. So that you can see here, this is the phi and this is the theta, okay, and this is the r. So r can be 0 to infinity. And here we have relation between how we can write Cartesian coordinates in the spherical coordinate system or a spherical coordinate system in the Cartesian coordinate system. So r equal to root under x square plus y square plus z square. And similarly, we have theta tan inverse root under x square plus y square by z, and phi equal to tan inverse y by x. Okay, and here in case of spherical coordinates, here we are concentrating more on the spherical coordinates. Okay, so spherical coordinates, we have differential displacement. So here we have dr, r d theta, and r sine theta d phi. So this is the unit vector ar, a theta, a phi, and differential surface area. So that ds, so this 3 is being multiplied here. Now if you multiply these two, you will get the radial that area vector is always perpendicular to the surface. So this is the AR, okay. And now if you multiply another these two, it will be along the phi. And if you multiply now this two, you will get this one. So like this, already you know that how to find the area if any coordinate systems are given. So here important is the differential displacement, differential surface area, and differential volume. So generally differential in case of if you talk about the cube or cuboid. So in case of cuboid, we are writing length into breadth into heights. So here also, what are the three different sides? Okay. So one is the dr, r d theta, r sine theta, d phi. So all are not sides here. We have like curve-like structures. So this one can be seen in this format. Okay. Then we have again 3D here. So one is the length of this arc, another is the length of this arc. So this is your r d theta, and this is the r sine theta d phi. So this angle is the d theta, this angle is the d phi, and this length is what radius is r. So finally, we are able to write the volume product of these three. Okay, so we have r square sine theta dr d theta d phi. So you have to make the diagram. Okay, after that you will able to write. So diagram is very important. Okay, then so here divergence theorem. So divergence theorem we are going to use multiple times. So it is give the relation between the surface integral and volume integral. Okay. So the what is the theorem statement that surface integral of any vector is equal to the volume integral of that divergence of that vector. Del dot represent the divergence. Next, Stokes theorem is also very important. Stokes theorem says the relation between line integral and the surface integral. So line integral of any vector is equal to the surface integral of the curl of that vector. So again, Laplacian equation, okay, del dot del v, del square v. So this Laplacian equation in different coordinate systems is very important here. We can write for the Cartesian coordinates, cylindrical coordinates, and spherical coordinates. So these are the important point here. Next, we have here from the Coulomb's law. So Coulomb's law, again, here we will have Coulomb's law. Simple Coulomb's law is what? It is the F equal to Q into Q1, Q2 by R square. But when we have to write this one in form of vectors, so in case of vector form, how we are going to write? Okay, so when we have multiple charge is placed in the system, so how this Coulomb's law is going to act? So in general, for the 2-point charges, it is directly proportional to the product of charges, inversely proportional to R square. So finally, K is the proportionality constant here. So that is 1 by 4 pi epsilon naught. And epsilon naught value is 10 to the power minus 9 divided by 36 pi farad per meter. So in case of this is the 2 points. So now if you're trying to write in the form of vector forms, so here, if you're talking about the force due to charge 1 on charge 2, then F12. And if you're talking about force due to charge 2 on charge 1, then we have F21. So here we are going to use the position vectors. So this R12 is going to be equal to R2 minus R1. So R2 is the final position at which we are going to calculate the force, and this is the initial due to which charge we are going to calculate. That's why we have R2 minus R1. And this A R12 is the unit vectors. So unit vectors, how we are able to define here? This is the vector and divide by magnitude of that vector is the unit vector. So finally, this one Coulomb's law, we can write in the form of vector. Okay, that is the important. And in case of multiple charge, this is the principle of the superposition. So we are taking the Q by 4 pi epsilon. Q is the charge on which we are trying to find the force, and Q1, Q2, and so on up to Qn are the charges due to which we are trying to find the force on the Q. So finally we have Q by 4 pi epsilon summation K equal to 1 to N Qk into R minus Rk divided by R minus Rk cube. Okay, so this is the Coulomb's law in the vector form. So again, we have some, can be, this is the 1 marks question also. What is the electric field intensity? So electric field intensity is what? It is the force per unit charge. So already we have seen F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So if we divide by electric field intensity at charge Q. So finally we'll get only one charge in the numerator. So Q1 by 4 pi epsilon naught R square. That is the electric field intensity. And very important is that what are the application of the electromagnetic waves? So electromagnetic waves, okay, applications of EM waves. So nowadays you are seeing that first thing is it is communication, where we are going to use the EM wave, or if you're talking about in the medical field, so we have MRI, magnetic resonance imaging. There also we are using the EM wave. Even if you'll talk about different applications, okay, even in the micro oven also we are going to use the electromagnetic waves. So these are the, can you say that it is the like important questions, objective questions also. And when we'll talk about electrostatics, electrostatic means charge is stable. So this is the electric field intensity. So now what do you mean by the charge distribution, or how we'll find the charge density? So charge density is what we have in case of line, we have charge density is different in surface in case of volume. So charge per unit, okay, per unit length is the rho L. Charge per unit area is the rho S. Charge per unit volume is the rho V. So this is the, again, you can think this one is the important 1 marks questions, charge density. So then we have, this is about electric field, okay. So we have again many important thing here. Application of the Coulomb's law. So here in between wherever we have Maxwell equations. So those Maxwell equations are also important. So next we have important thing is here Gauss law. Okay. This is the condition in case of volume charge, surface charge. Okay. Now electric flux density. So this flux density is what? D equal to epsilon into E. So total flux we are able to find the integral of D dot ds. Now very important thing is the Gauss law. So Gauss law is the very important here. So the total flux through any closed surface is equal to the total charge enclosed by that surface. So that's why total flux equal to charge enclosed. So here how we are going to prove this. Okay. So that is the proof, and here we'll get one Maxwell equation also. So this is the total charge. So this flux, total flux is the integral of d dot ds over the closed surface. So finally, by the help of charge density, okay, we have q equal to rho v into dv volume integral. So now if you use these two equations, so we'll have here charge equal to surface integral of d and rho v into dv. So what you are seeing that here, one is the surface integral, one is the volume integral. So finally, we have to use the divergence theorem here. So divergence theorem says that surface integral of vector equal to the volume integral of the divergence of that vector. So when this is going to happen, so if you will compare the previous equation, we have rho v equal to del dot d. So if they will ask you to derive the Maxwell first equation, so in that also Gauss law is important. Okay. Or if you have to prove the Gauss law in the point form, so here also, in that case also, this Gauss law is very important here. So this is the first del rho v, this all you need to remember. Rho v equal to del dot d is the Maxwell first equation. Like this, we have Maxwell another equation also. And this is the point charge. This is the very finite charge. These are the important for the external exam. Okay. And this is the uniformly charged sphere. So these are the important questions what we have seen. So Coulomb's law is very important. Then we have Gauss laws. Okay. That is also important. Next we have discussion about dipole. Okay. So energy density. So that energy density is again important question here. So this question you can have some long question also. Okay. So internal exam will have different weightage. External exam it will have different weightages. So this energy density. So it will be the long question you can expect. So we have what we are doing in this point charge. We are trying to bring from the space to in particular volume. So when this one is the empty. So when you bring the charge Q1 to the point P1, it's not going to feel any force. So that there is no opposition. So work done will be zero. When we are going to bring charge Q2 to the point P2, then P1 is already there to oppose this. Okay. Again, when we are going to bring the Q3 to the point P3, so it has charge Q1 here and charge Q2 here to oppose this. So like this, so finally we'll have work done to positioning all three charges. For the first one 0, for the second one Q2 into B21, this is the potential. Okay, from 1 to 2. Again, we have Q3. So B31 plus B32. From 1 to on 3, from 2 on 3. And again, if you are going to reverse this situation, so for the W3, so means first we are trying to bring the charge Q3 in the system, then W3 is 0. And if you are trying to bring now Q2, so already charge 3 is there, so potential will be B23. And when you try to bring the charge Q1, so already Q3 and Q2 is available. So that due to that potential difference B12 plus B13. Now both equation we are going to add. So here we have W equal to half Q1 B1 plus Q2 B2 plus Q3 B3. And this one we can write in general when we have multiple charges. So then W equal to half summation K equal to 1 to n q k into bk. So this is about the energy charge density. So energy density in case of electrostatic field. Okay. Energy density in electrostatic field. And electric field intensity due to infinite line charge distribution. So that was earlier in case of Coulomb's law. That is also important point of view. So now here we have another important questions. This is about polarization. So here we have continuity equation and relaxation times. So this both are important, continuity equation and relaxation times. So here this is based upon the charge density. So we know that current density is J equal to I by A. So rate of flow of current per unit area, that is the charge density. So finally we can find I equal to integral of J dot ds over the closed surface. And rate of flow of charge is what? Per unit time is the current. J is I by A. Current per unit area is the current density, and current is the rate of flow of charge per unit time. And this is the, again, you are going to apply the divergence theorem here. Okay. So J dot ds surface integral equal to volume integral of del dot z dv. And this is the from the equation 1. So now again, if you try to compare this, so this del dot j is what? It is the rho v from the Maxwell first equation. So that we can, so now this is here del dot j is equal to not rho v. What we have from the Maxwell first equation, del dot d equal to rho v. So this total charge, okay, so total charge will be given as rho v into dv. This is the charge density, this is the volume. So that's why in place of q is written as integral of rho v into dv. Okay, so finally we are trying to rearrange this. So now if you try to compare this equation, here we have del dot j from the equation 2, so this part, and here from the equation 3, that is the minus integral of d rho v by dot t. So finally, when this is going to be equal, when del dot j will be equal to minus dou rho v by dot t. So this is again very important term. So this equation is called as the continuity equation. So again, if we have about the relaxation time, so that relaxation time part is also important here. So Ohm's law is what? J equal to sigma E. So this is the, again, Gauss law if you are going to apply here. So del dot E equal to rho v by epsilon. So this one, how we are getting? We have del dot D equal to rho v, and D is what? Epsilon E. So finally, epsilon E and a rho v. So finally, if you take del dot E, so we'll get here rho v by epsilon. Okay. And now we can substitute the values. So now here in this, if you take this minus dou rho v by dou t same side, so this is the going to be equal to 0. This is called as the homogeneous linear ordinary differential equation. So now this one again, if you try to rearrange, okay, and I will integrate. So finally, we'll have ln rho v minus sigma dt by epsilon plus ln rho v. So this is the integration constant, okay. So finally, we can write rho v equal to rho v naught e to power minus t by tr. So this tr is known as the relaxation time, which is tr equal to what? Epsilon by sigma. So epsilon, you know, this is the permittivity, sigma is the conductivity. So relaxation time is here very important. And Poisson Laplace equations is very, very important. Okay. So here we have situation, already we have explained starting. So del dot D equal to rho v. Again, we are substituting the value of D. Then again, we have del square V equal to minus rho V by epsilon. So this is called as the Poisson equation. And limiting case of the Poisson equation is what? We have Laplace equation. So when rho V is going to be 0, so then del square V equal to 0, that is called as the Laplace equation. So whatever topic I am telling is important for the examination point of view, and for that separate video is also available. So if we are going little fast, you can see that. So in case of capacitance, we have three different situations: parallel plate, and your coaxial cable or cylindrical. And apart from this, we have a spherical capacitor. So this spherical capacitor is more important here. So here we are concentrating a sphere. Okay, so inside one sphere, you can think about another sphere. So finally, is going to form the, okay, like a two plates. So capacitor is what? Two parallel plates separated by some dielectric medium. So here one inner sphere, one outer sphere forms the capacitance effect. And inside this we have dielectrics. So inner sphere having radius A, outer having radius B. So finally here we have to take the Gaussian surface. On the basis of that, we are trying to find the capacitance of the spherical capacitors. So by using Gauss law, what is the Gauss law? Total charge enclosed equal to the total flux. So this is the charge, and this is the formula for the flux, and D value is substituted here. And here for this Gaussian surface, you know that area of the sphere is what? 4 pi r square. So finally, from here we can get the electric field intensity is E equal to Q by 4 pi epsilon r square. This is the unit vector. And now we have to find the potential difference. So a step is same. First we have to find the total charge. From that we have to find the electric field intensity. Then we are finding the potential difference. So B equal to in minus integral of E dot dl from 2 to 1. Okay. So this notification from the outer sphere to inner sphere. And again here, just now we got the electric field intensity, Q by 4 pi epsilon r square. And this limit is B to A. So integral of this one, again we have dr by r square. That integration we have to do here. And then we are going to substitute the values. So this integration, if you try to do here, what is the value? You will have integration of dr by r square. So this also can be written as r to the power minus 2 into dr integration. So finally here, what we are going to get in this situation, that sign will come here. Okay. So finally here we have 1 by r. So again, we are going to substitute the values, and this negative is going to come. For due to that, its sign is going to become positive. Negative, negative, this negative got cancelled. And its capacitance is what? C equal to Q by V. So substituted the values of V here. So finally Q got cancelled. So we have 4 pi epsilon by 1 by A minus 1 by B. If B will become very infinity, very large value, then capacitance C is going to become 4 pi epsilon A. So it is the condition when we have very infinite large sheet. So these are the important questions from the electrostatic parts. Okay. So Maxwell 2 equations are here important. And apart from this, we have seen important is spherical capacitance, spherical coordinates, and Gauss law and Coulomb's law in the vector form. Then we have another question, that is we have to find the Maxwell 2 equations also. And very important is the electric field intensity due to infinite line charge distribution. So electric field intensity due to infinite line charge distribution. So infinite, that line length is what? Infinite. So that is the question related to the line charge distribution. So here in this infinite line charge we have taken, it is along the AB. For that differential element is taken here B. This is also important question. Okay. So at point P, we have to find the field intensity. So we have to joining the A and B. And finally here we have alpha 1, alpha 2. and alpha is the angle between the DL and this point T. So again, we have to total charge. This is the charge density. So rho L, okay, from the length ZA to ZB. So here, what will be the coordinates? It is Z axis. So X and Y value will be 0. So DL is taken at Z dash, T is taken as the at Z. So on the basis of that, this position vector R is written as rho A rho plus Z minus Z dash AZ. And again, we have to find the unit vector. Okay. So finally, electric field intensity in terms of vector form we have written here, and again now we have to solve these values, how we are going to get the R. So this is the rho sec alpha and Z dash equal to OT minus rho T 10 alpha, and if you differentiate this, so finally 10 alpha is what sec square alpha. So once we substitute these values, okay, so finally we have rho L by 4 pi epsilon rho roots and inside the bracket minus sine alpha 2 minus sine alpha 1 a rho plus cos alpha 2 minus cos alpha 1 a z. So now if point have different situation, if point B is going to be infinite line charge. So in case of infinite line charge, B will have coordinates 0, 0, infinity. A also will go towards the negative side. So that will become 0, 0 minus infinity. So finally this alpha 1 will become pi by 2 and alpha 2 value will become minus pi by 2. So one will substitute this value. So cos pi by 2 value is 0. Okay. And sine minus theta equal to minus sine theta. On the basis of that, we have equal to rho L by 2 pi epsilon rho A rho. So this is very important expression. Okay. So these are the things from the electrostatics, which is the very important. Okay. Thank you. Thank you very much. Like, share, subscribe with your friends. Thank you.